So now that we've seen how continuous growth and decay functions can work within the context of compound interest, we have a lot more applications in using the irrational number e in science applications. Now, you can see here in this particular sample problem that we're using it for radioactive decay, the word decay model for carbon-14. And now we can see that the formula for radioactive decay is really the same formula as what we saw for continuous compounded interest, except we have this a to the o with a subscript o. Anytime you see a subscript with a 0 like that, all that's really saying is that it is the initial amount of whatever it is that we're looking for. And so in this particular case, if the amount of what it is that we're dealing with is carbon-14, a to the 0 subscript is the initial amount of carbon-14, and the a that we're looking for is the remaining amount of carbon-14 after the decay model has taken place. Now, if you notice in sample problem number 6, I'm going to let you do this in a second, the formula is 3.6 e to the RT, and you may be thinking to yourself, well, wait a minute, 3.6 does not create a decay model. That's a positive, that's values greater than 1, and so what it ends up doing is creating a growth model. But what you'll notice is right after that it says that the R is a negative 1.21 times 10 to the negative 4th, and so what you're going to have there is a negative exponent value that is actually going to create a fraction between 0 and 1, and that's where the decay is actually going to come from. So take a little time here for sample problem number 6 and actually read the whole scenario, read what's given to you, and see if you can apply that information and the formula at the top of the page to parts A, B, and C. Okay, so what we've got here is a formula, 3.6 e to the RT, with a rate, and that rate is written in scientific notation. And if you feel like you need to, you can go ahead and convert that to a decimal. You just work the decimal places backwards 4 places, and you're going to get like negative 0.000121, and you can use that in place of your calculation. But whatever way you need to do this. And so part A says, we'll find the amount of carbon-14 present initially after the kill. Well, at that point in time, 0 years have actually passed by. So we have a T of 0 initially after the kill. And so we have 3.6 E. And anything raised to a 0 power is just 1. So we actually have 3.6 grams of carbon-14 initially present immediately after the kill. Now, part B says how much C14 is left after 9,833 years, and then we've clearly gotten to a fossilization at this point of the actual bone, and so we're going to say that T is equal to 9,833 years, and we're just going to have the exact same setup. And then if you use your calculator effectively, you'll get an approximate value of 1.1 grams of carbon-14 remaining in the fossil. So this is a good use of the formula that we have here for continuous decay. Now it asks us to graph the model. Now the key here is really getting the scaling correct, and so I'm going to go ahead and set that up right now. Okay, and so you can see here for grams, I just used a single number, 1, 2, 3, 4, 5 grams, but for the time function I actually used 5, 10, 15, 20, but representing the number of thousands of years that have passed by. Now if you feel like you need to t-chart more points, that's perfectly acceptable. I've got 2 solid points from parts A and part B. So if I go to t equals 0, I'm at 3.6, and so that's our y-intercept. And if I go to 9,833 years, which is close enough for me to approximate to 10 years, that's going to be about 1.1 grams, and so I can approximate that. And I know that we're working with an asymptote, and so that would be a pretty good generic graph or sketch of this model. So, alright, there's a good application problem for continuous decay in reference to a science application.